Okay, today we're starting sine and cosine waves. It's a totally new idea. It comes from the unit circle. First thing I want to do is make sure you guys are comfortable with the unit circle, at least some parts of it. So here's 0 degrees, and there's the point 1, 0. I go counterclockwise around my circle. The points I'm really interested in today are 0, 1, negative 1, 0, and 0, negative 1, and then back at 360 degrees to 0, 1. Up here we're at 90 degrees, down here we're at 180, down here we're at 270, and we're back again at 360. Okay? Have I accurately labeled my unit circle? It's not a particularly well drawn circle. But is it accurately labeled?
Yes.
Double check my positives and negatives, I tend to mess that up. Alright, here's what we're going to do. Instead of representing this radius spinning around the circle on a circle, we're going to represent it a different way. I haven't labeled these axes x and y yet. Can I leave them labeled as degrees instead? Is that allowed? I hope so, because when we get something called polar coordinates, that's how we're going to do it. I'm going to change this a little bit. What if I decide to leave these axes just labeled as degrees and call this angle x? Can I do that? Sure. Might confuse some people, but here's what I want to do now. I want to make a different graph. This one is going to look something like this. I'm going to go back to calling this y, this negative y, this negative x, and this x. You might want to wait a sec to draw or label it, because it might be a little surprising what the units are. Here's what I'm going to do. I'm just going to go down to negative 1 on the y-axis and positive 1 on the y-axis, kind of like the unit circle. Now what I'm going to do is take this x on the unit circle, which represents the angle through which the radius is moved counterclockwise, and I'm going to graph these angle measures as points down this x-axis. Take these angle measures and make these points. As I do that, for a quick review, I'm going to change them from degrees to radians. 0 degrees is how many radians? None. 0 radians. We start there. 90 degrees is how many radians?
Pi over 2.
Pi over 2.
Pi over 2. Pi over 2, 1/2 pi. Again, I'm going to label this a specific way, and you may want to wait till I'm done to make sure I do it right. 180 degrees is how many?
1
Pi.
Pi radians.
Wait,
That should be good.
how is that? How is that pi over 2?
180 degrees is halfway around a circle. Pi radians represents the length of half the
why is it
circumference of a
there?
unit circle.
Why is what?
Why is that there? Because I said I was going to take these angle measures and plot them as points down the x-axis.
Oh.
That's why I called this angle x to begin with. I'm not spinning anymore.
Oh.
Going down the x-axis. What's 270 degrees in radians?
3 pi over
3
2.
pi over 2.
Very good. It's 3 times 90.
Is this like kind of like a circle but laid flat in a way?
Very good, Jen. Very good. It's exactly like a circle
So
with a flat.
it's 2d? Or
So you're pretty much taking
Or,
the
I mean,
circumference and then you're flattening it out.
Some guys are way ahead of me already. 360 degrees is
2 pi.
2 pi. Okay. Let's see what happens when we, as you guys so cleverly put it, take this circle and sort of flatten it out. I'm going to say y is equal to the sine of x over here. Let's say y is equal to the sine of x. If, as I pass around this unit circle, over here, what is the sine of 0? 0. Remember, on the unit circle, the sine corresponds to y. What is the sine of 90 degrees?
1.
So then on this graph, this is the point, pi over 2, 1. What's the sine of 180? 0 again. We'll label that one in a minute. What's the sine of 270, or 3 pi over 2? -1.
Wow.
Label this one because I know. Make sure you get the X's and Y's right. Whoa, missed that one. Put that in the wrong spot. That's 3 pi over 2, -1. And then at 2 pi, what's the sign?
Pi over pi 1.
0.
Oh,
0. Now, these dots have to get connected. And I could find some more points. I could talk about how root 2 over 2 is 0.707 and root 3 over 2 is 0.866, and you could label some more angles. But I'm going to let you take my word for it that this starts out coming up at about a 45-degree angle, curves up like a bell,
whoa.
goes down through there at about a 45-degree angle. It never really gets linear, but it looks like a line pretty close to there. It's actually less pronounced, less curvy there. I'm making it. And that isn't perfect, but it's a pretty good sine wave.
Is it like this?
Yeah.
Oh, okay.
And like you guys said, it's a little bit like taking the circumference
we
and
did
stretching
this.
it out.
Like, we did sine waves at the end of that.
You talked about this thing last year?
And then, like, they can switch, like.
Wait, did you get to amplitude and period?
I don't think so.
Okay, we'll go into that yet. All right. This represents, I'm glad you've seen it before. I won't need every split second of today that I thought. I don't think you have.
Isn't this kind of like, does this have to do with like sound waves? Like,
Sound waves can be represented by these. So many things can be represented by these. One way to think of a sound wave, well, a sine wave, thanks Jen, is it's the up and down motion of the y points on the unit circle.
and also
Yeah,
like
it's just a
light
circle split in
frequencies.
half.
Yeah.
So you
Well, this is not the shape of a circle. This is not a semicircular shape. So don't draw this as a semicircle and a semicircle. That won't graph the correct points. Yes, sir.
And then is this what the cosine wave will look like?
Nope.
I
Wait,
thought it was.
Hold that thought.
could
Yeah.
you represent like amplitude by that, like light frequency?
That's different.
So much. Anything.
Parabolas.
Anything. Basically, a sine wave or a cosine wave, which I'll get to in a sec, can be used to represent anything that happens over and over and over again. Okay? When I speak, it is a sound wave, and what happens is the frequency of the sound determines the pitch and a few other things about what you hear. So I tell my physics class, one of my worst analogies, that a sound wave is kind of like a little man running by and hitting your eardrum. And however many times he hits your eardrum per second is the pitch of what it determines the pitch of the sounds you hear. But while he's actually doing that, the same thing is basically happening to your eardrum over and over again, and you can use a sine wave to represent that. A cosine wave then. As you guys have seen this before, I won't linger quite as long, but in this case, I'm still going to have the x-axis refer to this angle here. The x-axis is going to be the changes in this angle.
Wait a minute.
So I'm once again going to go through 0, pi over 2, pi, 3 pi over 2, and 2 pi. And now, though, the y-axis is going to represent the cosine of x. It's a little confusing for some kids, but I think of actually the y value now is how far the point is left or right on the unit circle. Okay? So, over there in the unit circle, what is the value of the cosine when the angle is 0 degrees?
1.
1. So a cosine wave starts up here at +1 on the y-axis.
Wouldn't it just be the other way around,
Depends what you mean by the other way around.
like
Let's see it in a second. Cosine of pi, I want more data before I give into your guessing games. What's the cosine of 90?
0.
What's the cosine of pi? -1. What is the cosine at 3 pi over 2 or 270 degrees? 0. And what is the cosine at 360 or 2 pi?
It's like the U one.
It's like a U, sort of. Yes. You can know that every other one is going to be at 0, and you can know all the other ones are -1 or 1 on sort of the raw, unchanged sine or cosine function. These are actually the exact same shape. They just start at different points.
But doesn't it go back down? Because 2 pi is 0 degrees again, and the cosine is
These
1.
continue on forever. Very good.
They follow the same pattern.
They follow the same pattern forever. They repeat forever and ever and ever. They keep going on for as long as you want to model whatever situation you're talking about.
So that's how we know that you started up at 1 and not just.
Yep. Now, the thing is, we're going to start mucking with these, and we're going to come up with some situations where it's equally correct to model the situation with a sine or a cosine, depending on how you want to muck with it. And I'll start talking about how these things can be changed. These two are what I like to call parent functions. And I use that term for a lot of things, but this is the parent function. The parent function means it's the simplest version of that function. Okay? A parent function, I like to say, is just y equals f of x, where f of x represents a single operation. F of x represents a single operation. In this case, that operation is finding the sine or cosine of an angle represented by a point on the x-axis. Another parent function would be y equals x squared. That is the simplest parabola in the world. And all you're doing with that parabola is just squaring x. Okay? The child function, I like to say, no matter what you're looking at, is y equals a times f of b times x minus k plus h. These letters are a little bit different depending on what textbook you're using or what chapter you're in, some textbooks.
This looks familiar.
We did this last
these
year.
look-
This is h. This is like when we did the slope, like h plus k, and then like
Yep.
h is like the opposite or something.
Yep, and I switched, I did h and k different from Mr. Singer, so I'll warn you about that in advance. But I'm not changing at this point in my life. I'm older than him. He's young, he can change. But you know, he does a great job with this. But every function we look at for the rest of the year, when we get back to logarithms, exponentials, parabolas, cubics, all of them will follow this pattern. So will sine and cosine. So in a little while will tangents and cotangents and secants and cosecant functions, which we'll also look at. And these four things will do the same thing on every function we talk about. We're going to talk about two of them as they relate to sine and cosine, but I'll quickly define all four of them right now. A is something you multiply by all of your y values, what they would be in the parent function. B is something you divide all your x values by. We'll talk about how that plays out soon. All the x values of your parent function. K, as I use it, is a counterintuitive shift left or right. What do you think counterintuitive means?
It's like against your intuition.
Against your intuition, against what you think. So if there's subtraction in here, you're actually going to move to the right. Even though normally you would think that subtraction would mean move to the left. H is your hintuitive. That's why I use K and H that way. Shift up or down. These four things are true on any function that you can represent this way. You can represent any function this way. It may not look this way. You guys remember using completing the square to change parabolas from standard form to vertex form in Algebra 2? Does that sound familiar? So sometimes a function is thrown at you and it does not look like this. It takes a little work to get it to look like this. But once you do, these will tell you exactly how to graph it.
But I feel like last year, maybe I'm crazy, I feel like last year H was before K.
It was. I told you I switched the H and K.
Okay.
So
Wait, how do
hopefully
you
that won't bother you.
how do you do wait, B is divide all x by what?
Yeah. We'll talk by whatever value b is. And that's going to take a little while to get clear, but that's the one we're going to start with today. Okay, are you ready? Hoping I can erase this. But those 4 letters and what they mean, learn them, live them, love them. Learn them, live them, love them. Okay. Go back to this cosine, which I didn't erase here. On a unit circle, you go around the circle every 2 pi radians, right? Okay? So, after that, the cosine values start repeating. Remember coterminal angles? All the fun we have with those?
Yeah.
At 0, it's the same value as 360, is 720.
Yeah.
This is going to go on forever and repeat, so we really don't have to care about a certain part of it. That part of it is from 0 to 2 pi. Okay? So for a sine or cosine has a period of 2 pi. Do you think that's always the most convenient thing? Do you think everything you want to model always repeats every 2 pi units? That's probably not. I mean, you just did linear velocity or angular velocity of planets last night. Do all planets spin at the same amount? Have the same length day? That would be kind of odd. Okay, so these have different periods. So, for example, if I want to graph y equals the sine of pi over 2x. This b I said over there is what you divide all your x's by. Sines and cosines is a slightly better way to look at it. This pi over 2 is going to change your period. And the relationship is that b, the coefficient in front of the x inside your function, always equals 2 pi over your period. With a little bit of algebra, you can rearrange this to say that your period is 2 pi over b.
Where are you getting this B from?
b over there on my general function is always the coefficient in front of the x.
Well, what's your period?
Okay.
Period is how long it takes a sine wave to repeat itself. Now, for a sine or cosine, the period will always be 2 pi, but in this case, this one's going to have a new period. So what I said over there is b is what you divide your x values by, right? Okay, follow me on this one. Strain your imaginations for a second. How far down the x-axis do we go before this starts repeating itself? 2 pi. Same as the length around a unit circle, because that's where we got it from. So we go from 0 to 2 pi over 1 full period of this cosine. The sine also went from 0 to 2 pi before it started repeating itself. b is what you divide all your x's by. So if I divide 2 pi by this coefficient, it's going to give me the new period of this function. So on a sine or cosine wave, if there's a coefficient there, it changes how long it takes the sine or cosine wave to start repeating itself. So for this specific example, the period will equal 2 pi divided by pi over 2. Journey back with me to 5th grade for a minute, and remember that if you're dividing a fraction by a fraction, I can make that 2 pi over 1 times 2 over pi. Dividing by the fraction is the same as multiplying by the reciprocal.
We learned them in 5th grade.
Yep.
Oh my god.
So what I now have is a sine wave with a period of 4. How do I graph a sine wave with a period of 4? I'm glad you all asked that. Let me show you. Here's how I picture this. Works really well for some kids. Some kids aren't sure they like it as much. Now I haven't changed what's called the amplitude on a sine wave. Or in other words, that a value over there, the a that's at the front of every function, in this case it's 1. That doesn't change how high or how low this thing goes. So my sine wave is only going to go from 1 to 1. Now, let's go back, look over at this cosine wave again for a second. I should have left a sine wave up here, done the cosine example. But the period of a sine or cosine wave you can think of as being divided into 4 parts. Okay, I gave you 5 points to think about, but those 5 points created 4 spaces. The space from 0 to pi over 2, the space from pi over 2 to pi, from pi to 3 pi over 2, and from 3 pi over 2 to 2 pi. Okay? If you divide a sine or cosine wave into these 4 spaces, the behavior is the same no matter what the period is. From 0 to 4, can I easily create 4 even spaces?
Yeah.
What will the numbers be?
1, 2,
Take
3,
your time.
4.
I'll just add it. No, we're actually from 0 to 4, we're splitting it up, not from 0. Good. You're right with us on the radians, but now we're over here with our new period of 4.
1, 2, 3, 4.
I thought I was gonna be smart for a second.
Yeah, you are. So 5 digits. 0 to 4 creates 4 spaces, even though it's 5 numbers. Call that the fence post rule. If you want to put up 4 lengths of fence, you need 5 fence posts. That actually stumps people. Semi-regular. Okay, now here's the deal. This sine wave will behave exactly like the parent sine wave that I just gave you. This child will unsurprisingly look like the parent. But there's often differences between parents and children. Shockingly. So it's going to, instead of behaving the way a sine wave does from 0 to pi over 2 to pi to 3 pi over 2 to 2 pi, it's going to behave that way from 0 to 1 to 2 to 3 to 4, and that first chunk was horrible, so let me redo that.
That's the parent?
Nope, this is now the child.
How do you know how you're graphing it? Like, I know you know you're going to 4, but how do you know that it starts going up and not
Ah,
down? Is that because it's positive?
that's because it's a sine wave. What does a sine wave do on the unit circle first, Jen? It goes from 0 to 90 degrees, and at the end of the radius, you've got all positive y's. Then, it goes from 90 to 180, and those positive y's go from 1 to 0. So, in the first quarter of this sine wave, this goes from 0 to 1. In the second quarter of the sine wave, it goes from 1 down to 0, just like the height of the end of the radius does on the unit circle. From 90 to 270 on the unit circle, the sine value goes from 0 down to -1. So in this case, from 2 to 3, we're going to go down to -1 here. So if you have a coefficient in your y equals sine x function, if there's a coefficient in front of the x, your new period is 2 pi divided by that coefficient. And then you divide your graph into your 4 spaces with 5 fence posts, and you graph it the same way we graphed the first one. The shape will be the same.
Wait, what is B?
B is a coefficient in front of x inside a function, and if you have a coefficient in front of x inside any function, also being acted on by whatever the function is, sine of pi over 2 times x. Then you take 2 pi and divide it by that coefficient, and that gives you your new period. Divide that new period into 4 spaces and graph it exactly as we did. The first one.
How do you
What's
know it
F?
can only go to 1
Um,
on the y-axis?
We got this from a unit circle. A unit circle by definition has a radius of 1, so what's the highest and lowest that radius can go? 1. And on a cosine, what's the furthest left and right that unit circle can go?
See, I actually thought that was 1.
You know, it is. So on this cosine graph, notice we also stayed between 1 and -1. Now, if it's a cosine graph, this part can be a little disorienting for kids. If it's a cosine graph, then this actually represents how far left or right you're going on the unit circle.
Wait,
If it's a sine graph, this actually represents how far up or down you're going on the unit circle.
So cosine graphs are always going to start downward, and sine graphs are always going to start going upward.
Cosine graphs are going to start up and then go down.
That's
Yes.
what I mean, will
Yeah.
they start?
Well, now that's today. That's for tonight's homework. That'll work. Tomorrow, we're going to start talking about what happens when you move them left or right, and then they won't line up as nicely with the y-axis as this. But for tonight, that rule you just said will work perfectly. Once I start bringing in k and h, though, all hell breaks loose.
What
It's
are
complete
those?
anarchy.
Tonight we're not doing.
Tonight, no, we're doing period and amplitude. So I need to give you amplitude real quick. Any questions on period? Would you like me to do another period example?
Well, like, can we just say, can we do if sine was like 4x?
So sine was 4x. It's an excellent one.
I
Do
mean,
that
I
one.
know it's like.
Okay. I wanted to do one like that anyway. May I do cosine? Just to.
Oh, yeah.
Okay. All right. So
What?
this one's going to be annoying, but new example. Y equals cosine 4x. Okay? I did a lot of explanation here in terms of general functions and period, but now I'm just going to jump right to the important step where I say my new period is 2 pi over 4, which works out to pi
over 2.
Pi over 2. Yep, very good. I actually could have left up the old graph and relabeled it. This is where those of you who love fractions will have an advantage. I'm not going to scrunch everything up here, but that would be the effect of this. I'm going to draw pi over 2 out here. Show you guys a trick of what I like to do when you get fractions like this. What's half of pi over 2?
Pi over 4.
Pi over 4, 1/2 times it.
But isn't pi over 2 just 90?
Yeah.
So couldn't we just.
Right, 90 and 45. Now we're in radians.
See, we're supposed to transition to radians.
What's half of pi over 4?
Pi over 8.
Pi over 8. Once you split it into these sections, listen carefully to this part. Once you split it into these sections,
3 pi over
3 pi over
3 pi over
8.
Oh.
Very good. You guys got the trick before I even said it. Once you got the period, which is pi over 2, cut that in half, which is pi over 4, cut that in half, which is pi over 8. This point over here, your 3/4 mark, is going to be 3 times whatever your 1/4 mark is. Your 75% mark is going to be triple your 25% mark. So that's 3 pi over 8. So whenever I get a new period for one of these, I always write the full period, then the half, then half of that, triple that one, and that's my 3/4 mark. It's my little trick. From here, it behaves exactly like the other cosine wave. It starts up here at 1, but instead of taking 90 degrees, or pi over 2 to get down there, this gets down there in pi over 8 degrees. It's -1 in a mere 45, or pi over 4 degrees. It's 0 again at 3 pi over 8, which is 3 times 22.5, 67.5 degrees. And up here at 90 degrees, it's back up at 1. The whole thing's a little crooked, but that's basically the shape. Here's my rule for grading these things on your tests and judging them on your homework. If your drawing is perfect, woo! If your drawing's not perfect, I will go by whatever you label. So if you don't think your drawing is super clear and incredibly clear, I would suggest labeling these points. Well, maybe not labeling. Clearly label where it hits the x-axis, but don't necessarily label your 0. So I would get in the habit of clearly making sure your tick marks are clearly labeled at your intercepts and labeling any non-intercepts. Unless your drawing is absolutely fantastic and looks like it was made by a computer for the purpose of being printed in a textbook. And then don't bother to label anything. I'll be perfectly happy if it's that good. Is that a clear standard?
Yeah.
Okay. I had a colleague, Michelle, who I loved his analogy for this. As this gets bigger, it's like fast forwarding a film. When this coefficient is greater than 1, it's like you're fast forwarding a film, you're speeding everything up. Okay? Because if I had drawn from 0 to 2 pi here, this whole cosine wave would have just fit in the first 25% of it. It would have been scrunched up, like watching a film go faster. And if I did multiple periods of it, it would have looked like an earthquake was coming on the seismograph. Which does make use of this thing. and logarithms mixed all together. In this case, going from 1 to 4, well, 2 pi is actually 6.28. This also fast forwarded. If this is less than 1, and pi over 2, just so you know, has an actual value of about 1.57. So this is still greater than 1. We still sped up the film a little bit. But if you put something less than 1 in here as a coefficient, well, when you put something less than 1 in the bottom of a fraction, it makes the whole fraction larger. So that would be like watching the film in slow motion. Your sine wave will get stretched out longer. So somewhat counterintuitively, decimals and fractions less than 1 here will make your sine wave or any function stretch out. Greater than 1 for your coefficient will scrunch things up. That won't always be easy to see because sometimes you'll just draw the same sine or cosine over and over again and just relabel it. But if I had consistently labeled my distances, you would see scrunching up of both of these sine waves. Just enough time to do amplitude. Any questions on this, either of these examples? The steps for tonight are take this coefficient, your new period is 2 pi over that coefficient, mark that period, divide it evenly, put the same points in that you would on the first sine and cosine wave we did. Questions, comments, concerns, or compliments on these, on period?
Later, I guess you don't have time, but.
Not right, I can't redo another one right now.
No, but the algebra, I don't. Never mind, I'll get
Okay.
back to it.
Gotcha. Yeah, we'll review some of these steps. All right, amplitude is easier, that's why I saved it.
How much board space are you gonna take?
Good question. Probably just this board, we'll see, but I've got to do some graphs. Amplitude. Y equals A times sine x. This is the one you multiply by your y value. So you multiply by your y value. So all this does is stretch your sine or cosine wave like taffy.
Wait, what is A?
A is, in this case, it is amplitude. Thank you. On any function, we don't call it amplitude on every function, but on every function, something that is being multiplied by the entire function. It is outside the operation. Whatever the operation is. Squared if it's a parabola, cubed if it's a cubic, sine if it's a sine wave. Outside the operation, it stretches all your y values up and down.
So it's something you can't see, or.
Now you can see it, it's right here.
Well, I mean, you can define it in the equation, but not on a graph.
Sure we can. Y equals 5 sine x. Have I made any changes to the period? No. So what will the period of this sine wave be? Exactly. All right, there you go, 2 pi is exactly reciprocal. No, not exactly reciprocal. Anyway, sorry.
So wait, if you have x, you just assume it's 2 pi?
If you have x, you don't assume anything. You're being told that it's 2 pi. Because you know that a sine or cosine repeats itself every 2 pi, and your b value is 1. So if you just see x, you're being told there's a 1 there. Okay, what you assume is there's a 1 there, and once you assume there's a 1 there, then you know the period's 2 pi.
Oh, so you always give us A.
I'm like, well,
Sometimes
before
you
the
can
next
find
test, I'm going to give you like a situation, and you're going to come up with the equation. But I'll give you A in one form or another. In this case, I'm just going to, instead of putting 1 and -1, I'm just going to put 5 and -5. And I'm going to go out to 2 pi, halfway to pi. Half of that's pi over 2, triple that, 3 pi over 2. And it's a sine wave. So as Jen pointed out earlier, sine waves start at 0. And again, my drawing's horrible, but you know what? I'm not going to change it because I'm taking a test and then I'm in a hurry. So instead of changing my drawing, I'm just going to label pi over 2, comma 5, 3 pi over 2, comma -5, and I will grade you based on your labels. Your drawing would have to be pretty bad for me to take off points if you labeled it wrong. So that's all you do with amplitude. Change your height and your depth, or relabel your axes. Again, once we add h and k, these get much more exciting. Any questions on amplitude? seeing another one be helpful or better? Okay. Pick a number for cosine.
3.
Okay. Y equals 3 cosine x. We've not changed the period, and I think I don't think in your homework tonight, I don't think they mix and match. I don't think I signed anything where they mix and match. Okay, Jen, since the amplitude is 3, now instead of bouncing between -1 and 1, we're going to bounce between -3 and 3. I'm just going to label those points on my axis. I haven't changed the period, so this one will be 2 pi. This is still just a once around the circle. This is like finding all the cosines on a 3-unit circle instead of a 1-unit circle, if we made such a thing. Pi over 2, triple that, 3 pi over 2. As Jen pointed out earlier, cosine starts up at its maximum and goes down. Winds up back at its top. Please don't forget that it does go on forever, but I usually only ask you to graph 1 period. Your homework tonight may ask you to graph 2 periods. Actually forgetting. So this is the point pi -3. My zeros are clearly labeled by their tick marks. And 2 pi over 3 I felt the need to label. And that's 0, 3. You can tell it sits on the y-axis. You guys can handle that? I believe you can. Homework tonight is over here and online. It is page 372, 17 to 22 all. It was online with the same page number, with the wrong page number until this morning when I caught the mistake and checked it and changed it. So if you filled in your planner from what I had up last night, this page number is different. Questions, comments, concerns, or compliments?
We just gotta draw the graph.
I believe it's mostly graphing in the homework tonight. You may also be shown a graph and have to answer questions about it. But sometimes I give it to you forwards and the homework asks you to do it backwards. All right, Daryl, go ahead and kill it.